Welcome back to Behavior-Based Robotics. Today we will talk about hybrid architectures. We've seen the benefits of reactive architectures, but we have also seen that it's quite hard to add some deliberative elements to it. And today we will see how we can incorporate such deliberative elements into the architecture. So, what the goal is of today is that we understand the limitations of other approaches, that we also see from biology that some good examples can be learned. We have to understand that incorporating deliberative elements into behavior-based elements is not that easy, and that you have to understand what you have to do for that. And we study several examples because deliberative hybrid architectures are the most common architectures in the end of the 90s. Okay. What we see is that we were thinking about purely reactive systems. The nice thing of such a purely reactive systems is the world is the best model you have. It is consistent, it's stable, so often the intermediate sensing is perfect to have a good response. Yet, that's good if the robot is wandering around headlessly, but at the moment that you have to localize the robot and give him a task a little bit further away, and for instance, if you have a space robot that can be really, really far away on a different moon, then it's quite hard to do everything reactive. If we do everything from the eyes of the ears of a robot, then concepts where we're working with as humans, symbolic knowledge, that's not really a value. And sometimes you want that this symbolic knowledge is of value. For instance, if you have two bottles on your table, one was sour, one was sweet, then you have to know what the symbols are meaning on those bottles, and if you want to have the sweet bottle. So, if you look to biology, there we have the Norman-Shallice Model, and there we see that we have two types of control, and one side you have the willed control, the conscious control, and on the other hand the automatic control, and that executes without awareness with several different activities that are executed in parallel, and they can even start without that you be aware of it. On the other hand, there is the conscious control. That starts with awareness. You starting to be aware of the situation, and you're starting to focus on it. That means that part of what you're doing gets your full attention, and that means that you start also to make some plans for that. That you start being aware what works and what not works of all the actions you perform, and you even be starting to aware that some of the actions maybe are not that wise and are maybe even dangerous. So that are great to take control of your habits and to learn new skills. But once a habit is fully learned, it's quite hard to relearn it. So it's difficult to apply willed control. Norman-Shallice made a model for that. On the right side, you see a number of different robot schemas. In that sense, it was still a psychological model, so it was a psychological schema. And each of those schemas can lead to actions, the arbiter with the model. But which action wins, that's partly with it, influenced by the two wires that come from above, and that is the willed control. And on one hand, that's attention. So with it, which one is under control, and if you have attention, you have a bigger chance to get access to the actions. And on the other hand, there's also a lot about motivation, if you're afraid or hungry, or et cetera, et cetera, et cetera. So you can influence your effects there. With this model, there is a connection between deliberation and activity. That means that you can use deliberative schemes to model out both the attention and which schemas get under control. Still, the schemas compete against each other, even when you're training with it to read a book. If a tiger shows up, then with it you start running anyway. If the incentive is large enough. So what you see here, and this is something that came up from psychology, is that the selection which schema is active. That's precisely the thing that under deliberative control. And several neurophysiological experiments have been performed that show that there is quite some truth behind this model. So in this sense, we have seen a hybrid architecture from nature. So we would look on different architectures. In robotics, mainly with it, we have deliberative architectures before with it, the 90s. And there you see that you have a number of actions, but they are controlled from top to the bottom. The top is fed with a center cue that partly see what immediate interpretations could be made and where you can react on, but they also build up a local world model and a global world model. And both on the global world model, you have strategic planning. There you give a certain tasks with your tactical planning. You decompose in a number of actions. Those actions are still also planned with short-term local planning, where you get access of the parameters of your actions, and then if you have made your action plans, then you execute them with the controller, which is based on the immediate signals you get from the sensors. So, what's the strength of this approach? You have deliberative planners that can look far ahead, but they rely heavily on world models. So you have to be sure that you have a way to create very detailed world models. What's also great is all the a priori information you have from the world. You can incorporate it, including context, and you can have a far more broader perspective, and you can incorporate all the knowledge we have from the world. So that's the strength of deliberative approach. From the behavior-based also has quite some benefits, as we've seen before. One is that you can develop each module on its own. Once it's created and tested, it can show a very fast and robust performance in a dynamic world. You can combine all those different modules to quite complex behaviors that show quite intelligent emergent behavior. But still, they are coupled to the real world, so they are with it never astray, but also with it never very, very with it complicated. So the nice thing is if you can combine those two worlds, and you can do in several ways. One of them is do it hierarchical. What standard approach is that the lower levels are the reactive levels, and at a certain moment you have deliberative models. What you see is that once you have to make the jump from deliberative to the behavior-based approach, that you have a lot of interface problems, how to translate that knowledge. Another way is that you do it in two ways. On the one hand, you have a planner that always looks ahead, simulates what's going on, and thinks about what can happen. And based on those predictions, you're starting to tune some of the parameters. So you're not giving commands from exchange commands and sensors, but you are tuning the parameters and the configurations for the reactor. But for the rest, the reactor always continues, only with slightly different settings. And on the end, you have a very tight coupling between the planner and the reactor. And what you typically see is that you use the planner as a sort of a virtual sensor that can see the future. So you can combine it in three different ways, but for all that you need a slightly different interface strategy. First one is that you see planning as a way of configuration, how your behavior-based system works. The other way is at advisor, where you see the planning as a sort of a sensor and gives advice if it's better to go left or right. Adaption, that's tightly coupled to the schemes, where you learn from experience, and based on that you let the planner suggest and slightly with it a new setting of your controllers, and in that sense you always with it adapt and learn to execute your behaviors better. And last is that you see it completely out of bounds. So if you're stuck with your behavior-based systems, and as we know, you have strange attractors in your environment, and your behaviors can get stuck at certain moments, you can notify that because you don't make any progress, and then you can fall back to planning, ask the robot, stop with what you're doing, and start to think. You can then come up with a complete new plan and execute it. Okay. We give an example in the previous section about what sort of interfaces you can build and what sort of configurations you can make. And we will now look on different examples from robotics, how they actually did it. The one hybrid architecture that it's most famous, but also most famous because that was based on the famous author of this book, is Aura. And there he saw planning as configuration. He integrated his behaviors with an A-star planner that was able to plan paths, and those paths could be integrated with schemes. And as you know, schemes control the robot with it having a force field. So the path that an A-star planner was planning could be easily integrated with the controllers. And by separating the planning from the actually execution, you have both modularity, flexibility, and adaptability. So how does that architecture look like? In the middle you have the user that could communicate with the system, providing goals, indicating what could be done differently, even take over control of the robot for a short while, but also to monitor the process. On the left side, you have the learning part, where they recognize precisely what all the plans are that the user wants the robot to fulfill, and what can be learned from that. It also sees what different opportunities there are, if there are shortcuts possible, and based on that, you could do some online adaptation. So on the right side, you have the real control of the robot. On the lowest level, you have the reactive component that actually executes all the active schemas of that moment. And above that, you have three different level of planners. On the highest, the mission planner, then the spatial reasoner, and on the end, a plan sequencer, where you think about what to do when, and not always to have the same robot scheme active, because you can also choose between different reaction schemes depending on what is relevant at that moment. So another example of a hybrid architecture is the one from GUT. Here you have the three with layers: the controller, the sequencer, and the deliberator. And those two are isogramms coupled to each other, so there are no dependency on the timeline of the controller and the deliberator. What you see here is that it's, planning is not seen as a configurator of all your behavior watch is active, but more as virtual sensor that gives advice where to go next. And the nice thing of the Atlantis architecture, that it's tested on many NASA robots, and there you also see the real benefits of such a hybrid approach. So, in principle, the one that's in control is the behavior-based controller that purely reacts on what it sees and what it does. Below that, you have a sequencer that constantly builds up a pipeline of commands that could be done next, and which actions to take with it next is done by a deliberative planner. But what you have to realize is that it's done for robots that are in principle sent to Mars. So what you want to be sure about is that such a robot, when it's on Mars, that it also always has a filled pipeline with things to be done. At the same time, you want to be sure that those actions in the pipeline are safe and there is not one of them that it's dangerous. So you want to plan ahead and make sure that each of those actions is actually executable. So they started in the backyard of the NASA research laboratory JPL, and starting to build a number of robots that ended in Sojourner. That was actually sent to Mars. And what you see is that it's here running around on Mars. On the left side, you see that it went for a ramp of the lander, and that's why we have footage of its first exploration from the place where it landed on Mars. What's nice of this hybrid approach, that in the beginning everything was planned. They never know what would work, because such a design was never active on a planet like Mars before. So they have to know what worked on which surface. And actually what they had most difficult with is everything is red on Mars, and in a hard way they learned what was a soft surface and what was a hard surface, and you could make far more progress on a hard surface. And every time, because the mission was only funded for half a year, and the robot was functional after half a year, the engineers were allowed to make more and more advantage control systems available, what meant that the robot was allowed to, for a longer time, to work on its own. So in the beginning, they only traveled 5 meters a day. On the end, they traveled 5 times as far, because based on experience, they trusted the robot more and more to explore on its own. And that's the nice thing of the hybrid approach, that you can give more and more autonomy to the robot. So another example is the Planner-Reactor Architecture. Here you see that you have a tight coupling between the planner and the reactor. Every time the adaptation is performed, and directly when you see some performance drop, then the planner starts tuning the different parameters, and that means that directly it's adapting to the circumstances. This is built on the robot schema model, where they have a model for each different object that you can see in the world, for instance a table or a chair. But every time that you encounter another chair, that you use the previous knowledge, but also adapt to this typically chair. So this was tested not on chairs but on assembly cells, where they learned to grasp different objects. And there you can see how it looks like. You can even start doing some planning where to grasp it, but how heavy an object could be and how the weight is distributed, you cannot know, and that was actively adapted by the Planner-Reactor Architecture. So here you see that those two are directly coupled, and what's the nice thing is that the reactor is talking to the planner with perception, and you have a lot of things on how well you are doing, so information on the meta level, and based on that, if you see that an object is starting to drop out of the gripper, then you can start to add some extra force to it. So this was built with a finite state machine, and where you see is that each of those different modules have its own control loop, but you see on the top you have also an adapter where you are starting to tune the parameters of the reactor performance, and in that way you can adapt to the circumstances. Okay, we continue. As I said, hybrid architectures are demonstrated on a lot of different robotics systems. So we continue with Georgiev and Lansky. That's an example where you put the planning outside the loop of the real control. But what I think is that all the parameters that you need to fulfill an action, you actually know only at the moment that you have to execute them. So that means that you only start planning when all the parameters are available by your sensors. And once you have all the information available, then at the last minute you starting to make the plan what you sort of behaviors you should show at that moment. This was tested on the flaky robots, and later on developed further in the Saphira robot. And what you see is that you have a central database with everything that the robot wants. You see here nicely that they worked with the belief, desire, and intentions architecture. That is a way of saying what sort of belief you get from everything that you see from the world. You expect your goals with different desires, each with a certain weight to it. And once you have weighted all your desires, you come to a certain intentions, so the goals you want to fulfill. And each of those intentions are coupled to behaviors that make sure that your attentions are fulfilled. And those attentions you can also broadcast to the other robots, that the other robots or the human knows what your intentions of your robots are. So this is further developed in the Saphira architecture, and that was the basis of the Pioneer robot. And the Pioneer robot is the most used four-wheeled research robots that you can see in many of our robot labs. I only worked with it in simulation with it, but Tino and my colleague from Oxford were actually used those type of robots for multi-robot exploration. What is special about the Saphira Coordination is that they used not fixed rules but fuzzy rules, that you first translate all the percepts that you see in fuzzy membership. So you are a little bit tall or a little bit small, and based on that you decide on certain rules. And you can say a little bit to the left or a lot to the left. And once you have decided what to do, you can then defuzzify that again in actually what means a little bit to the left in velocity and in steering angle. So the last but not least example of the hybrid architecture is Cornell's architecture. because he actually implemented a subsumption architecture, but above that he also implemented symbolic level. And those symbolic level applied it to where to go next. And that was tested again on TJ, the robot that could pick up the soda cans. And that's an example from how the deliberative planning was coupled to the subsumption architecture, but there are more examples of behavior-based couplings, as for instance the BERA. What's specific with it on BERA is that there the specification is not on the sensors, but on the actions. Every behavior sends out its votes with an histogram where it likes to go. That can sort of seen as potential fields that can be summed by each of the suggestions that are made, and based on that you can try to find the maximum, and that's the best action to take on that level. So I talked a lot about examples of hybrid architectures, but I'm far from complete. Here is a list of actually different hybrid architectures that are tested, and the conclusion of all this exploration of hybrid architectures, that this is actually the way to go, that you should couple deliberative elements with reactive elements, but how to do that, that is the hard way, and they tried several ways to doing it. This are even still some more examples. What's most important is that you have to encounter dynamic systems. That means that you have to do some local planning, and that you have to plan your motions on the nearby circumstances. That means if you have planners that can work comparable with the sort of information your sensors give, then you can easily combine that, and that's the way to control your system. And in that way you can translate the goals that a deliberative system can have to behaviors. One of them is a goal-seeking behavior. The goal is something that you have planned, or the avoiding behaviors where you have seen obstacles that are given from the map that you've built up, so you know on forehand which obstacles to avoid. And if you have such a factor-based approach, then you can make compositions, and you can combine planning with sensing information. And in that way, if you have two obstacles in red, and you have a goal where you have to go through, then with planning you can plan when you still have enough space to go in between those two objects, or when your robot should go around. Okay, so these are even more hybrid architectures where we could go into. As you see, it's quite an extensive list. But what I want to wrap up to is most of those architectures, they see planning as configuration. So what sort of robot schema to apply at that moment. On the other hand, it also sees it as a resource, so as virtual sensor. What is not demonstrated as much as we would like is that it's also the basic of an adaptation. So that's the idea of the robot schemes, that every time that you execute a robot scheme, that the robot gets better and better and better based on that experience. And why it is not shown that often? Because this sort of transfer learning is quite difficult, and it's hard to get the one experience to the other one. So what we see is deliberation is quite handy. How it's used most often. So the controller can combine with force fields all those control signals, but if you have to do a sequencing to come to certain, to fill a mission, and you have different circumstances, planning is great for that. And when you see that you can make any progress, then deliberation is also great to do error handling, because it's clear that if you leave the behavior active, that no progress is made, and then you can think of a completely new plan, and you can take your time for that. So, thank you for your time to listen to this lecture about chapter 6 of the book Behavior-Based Robotics, and I hope to see you next time.